I'm presenting my screen. So in the previous class, we had seen the speed torque characteristics of a shunt wound DC motor, correct?
Yes, sir.
We had seen some basic equations. I have those equations here. V is equal to V plus IAR, E is equal to K phi omega, where K we knew was a constant once the motor was constructed. We had substituted this and we had obtained speed omega is equal to V minus IAR upon K phi. Also, torque is equal to K phi IA. We had seen that if we are using the SI system of units, and then both the constants are the back EMF constant and the motor torque constant, both of them are same. Then we had substituted this and we had seen that the speed torque characteristic of a shunt wound DC motor is the equation of a straight line whose y-intercept is given by V upon K phi. The slope is given by minus R upon K square phi square. The no load speed is given by omega 0 is equal to V upon K phi. The change in speed or drop in speed, change in speed is minus T R upon K square phi square. Drop in speed is T R upon K square phi square. And you say drop in speed, the minus n automatically goes inside. So the speed omega becomes equal to the no load speed minus the drop in speed. We had divided both sides of this equation by omega 0 and then del V, that is del omega upon omega 0 is equal to omega 0 minus omega upon omega 0. We had seen that this is similar to the slip equation in an induction motor, although there is no physical concept of slip in a DC motor. Okay, so today's topic is construction of shunt wound DC motor speed torque characteristics. Construction of shunt wound DC motor speed torque characteristics. So when we are drawing the speed torque characteristics of the DC motor, on the y-axis we have the speed, that is omega, and on the x-axis we have the motor torque, capital T. We had seen some characteristics in the previous class. This one, we can say that it is a characteristic with the armature resistance, only the armature resistance, no external rheostatic resistance in the circuit. In that case, this characteristic will be called as the natural characteristic of the motor. If we insert external resistance in the motor armature, in series with the motor armature, the no load speed of the motor does not change, it remains the same. However, the slope of the characteristic increases, and then this will be the nature of the characteristic for some resistance R1. If we further increase the resistance, this will be the characteristic for some resistance R2, which is greater than R1. If we further increase the resistance, this is the characteristic. If you go on increasing the resistance, the slope goes on increasing. Okay, is this clear, everyone?
Yes, sir.
Yes, sir.
So these were the speed torque characteristics of the shunt wound DC motor that we had already seen in the previous class. Today we have to see, actually not today, this will require 2 classes. We have to see how to construct these speed torque characteristics. Okay, so I'll start with the natural characteristic. I'll remove all the other ones. Okay, so the question is how to draw the speed torque characteristics. No, it is not just a question of taking a scale and a pencil, drawing 2 lines, one along the y-axis, one along the x-axis, and then one horizontally slanting line, and we say that yes, I've drawn the speed torque characteristics, and it is not like that. How to draw this characteristic? Can anyone tell me? What do you need to draw this characteristic?
By adding a external resistance, we will measure the rated speed. We will run the motor in rated torque, and we will measure the speed.
No, this is the natural characteristic. There is no external resistance here.
Sir, we need to vary the torque of the motor.
We need to vary the torque of the motor. Okay. Anyone else?
So we need to vary the armature resistance through rheostat.
There is no rheostat. There is no rheostat here. How will the torque change? Will it change because of rheostat?
By
No, the
By
first,
changing the
So we have
current,
to
the basic
by changing
question,
the current.
first basic question. How will the torque change?
by applying the load. By varying the load.
Yes, by varying the load, the torque will change. Correct. Okay. So what do you need to draw this characteristic? You take a motor, connect it to a load, continuously change the load, find the torque and the speed. Will you do that?
we have to run
Yes,
the
sir.
motor
Yes, sir.
in
Yes, sir. Yes. We will
rated
varying the
voltage
load
and
of
rated
we will
current.
varying the load of DC shunt motor.
So we can vary the current, armature current.
You can vary the armature current. How will you vary the armature current? Abhishek, how will you vary the armature
Actually,
current?
so by changing the load, we will
Yes,
see the
when you change the
variation in
load,
armature.
when you change the load, the torque will change and the armature current will change. Correct? Initially, what is the value of the load here
Here
at this point?
zero, zero, zero.
Correct. This is the no load speed. As you go on increasing the load, the armature current will go on increasing, the torque will go on increasing. Okay? This is the, what do you say? This is the direction in which this will move. Okay. So once again, my question is, how do you draw this characteristic? Will you apply a load and continuously go on increasing the load and plot the points? Is that how you will do it?
Sir, we have to run the motor in rated voltage and rated current, and then we will vary the load.
Rated voltage and rated current. How will, if you vary the load, the current will change? Or are you planning to keep the current constant?
The flux must be constant.
Flux must be constant. Flux is constant. No, when you say that you apply the rated voltage and the rated current and you vary the load, then the current is going to change. Because the torque is proportional to flux and armature current, and your flux is constant here. If you vary the load, your armature current will change. Okay, anyone else?
So if we take,
Sir, we will decrease the load and take the reading, sir.
Decrease the load and take the readings, increase the load and take the reading. It is the same thing.
so we will take 2 points and connect the line.
Yes, that is the answer that I am looking for. And you have learned in school that to draw any straight line, all that you need is
2 points. Sir, 2 points, sir.
So why to continuously change the load when all that you need is 2 points? Okay, is this clear? What do we need for drawing this characteristic? We need any 2 points on this line. Now the question is, which 2 points will you take? The first and most obvious choice is this point. What is this point?
No load point.
No
Without
load point.
Correct.
without load.
This is 1 point, that corresponds to the no load speed of the motor, where torque is equal to 0 and the speed is the no load speed, that is omega 0. What will be the second point?
At rated torque.
Correct. So let us say this is the rated torque of the motor. Okay. So the second point that we want is this point. These are the 2 points that we are looking for to draw the speed torque, to draw the natural speed torque characteristic of the motor. Remember that this is the natural speed torque characteristic. There is no external resistance in the circuit at this point. Okay. Okay, so to construct the speed torque characteristic, all that we need are any 2 points on the characteristic. Now those 2 points, the most convenient 2 points to be obtained are one corresponding to the ideal no load speed, at this point where the torque is 0 and the speed is the no load speed, and the other corresponds to the nominal or rated electromagnetic torque, where T will be equal to T nominal and omega will be equal to omega nominal. Okay. At this point, capital T is equal to T nominal and omega is equal to omega nominal. Okay. We're using nominal instead of rated here. Nowadays, we don't use nominal, we use rated. Okay, is this clear? Now, the next question is how to obtain these points. How will you obtain this point? How will you obtain this point?
So from the data on the sheet of the motor, it is written, means
Correct.
on the motor it is
Nameplate.
written the rated
The
speed.
nameplate of the motor will give you the
Nameplate.
rated speed.
Yes, sir.
Nameplate or data sheet of the motor will give you the rated speed, that is omega nominal, and from omega nominal you can find the nominal torque. Is that correct? How will you find the nominal torque from the nominal speed? By using the equation where is the equation? Yeah. Torque is equal to this K phi is C. So we'll see later how to find the value of C. So if you have the value of C and you have the rated armature current of the motor, you can obtain the rated torque of the motor. So the rated speed is obtained from the nameplate of the motor, and the rated torque can be obtained by using the equation rated torque is equal to C into the rated armature current. Okay, is this clear, everyone? Any questions here? Okay, then we come to this point. Yes.
Sir, in practice also we prefer that to get this first point, that is no load speed only.
Yes, this one, na?
Yes, sir.
This is the most convenient point. This one is, you can have doubts about this point, but there are no doubts about this point. Because
sir, actually, yes, sir.
Because at this point, the torque is 0, the load is 0.
So actually I'm asking, yes sir, actually I'm asking this because in case of DC series motor, no load speed is very high.
No, we are not studying DC motor. We are not studying DC series motor now, na?
Yes sir, but sir, this speed may also be very high. That's why I'm asking.
No, this speed is not high. Actually, this is the reason why we have compound motors. Correct?
Okay.
To limit the no load speed of the motor. Okay.
Okay, sir. Thank you.
Okay, so this point, we obtain the rated speed from the data sheet of the motor or nameplate of the motor, and the rated torque is found by using C into the rated armature current. So this point is obtained. As far as this point is concerned, here the torque is 0. All that we need is the no load speed, omega 0. And we have already seen that no load speed omega 0 is given by V upon K phi. omega 0 is equal to 1k Not what we can do is we can multiply both numerator and denominator of this equation by the nominal speed, omega nominal. So if we do that, I should have, I was a little late today. I should have written these equations already. If we do that, what happens? We are multiplying both numerator and denominator by omega nominal. Okay. So numerator will become v multiplied by omega nominal, and denominator will become k phi multiplied by omega nominal. What is k phi multiplied by omega nominal?
EMF. E.
Correct. Is the back EMF, and because we are using rated values, this will be the rated back EMF. Okay. So v upon e nominal multiplied by omega nominal. Now this e can be replaced by, what can I replace e by? Can be replaced by v minus
IRA.
and again so because we are using E nominal, it becomes V minus IA nominal, or the rated armature current, multiplied by only the armature resistance, no external rheostatic resistance. So the no load speed becomes V upon V minus rated current into armature resistance multiplied by the rated speed. Now we already have the value of V, that is the applied voltage to the motor. We have already obtained the value of the rated speed, and we also know the value of the rated armature current of the motor. So the only thing required to calculate the value of omega 0 is the armature resistance of the motor. Is this clear? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now the armature resistance can be determined approximately by assuming that half of all the motor losses at rated load is accounted for by the armature copper loss. Okay. What did I say? The armature resistance can be determined approximately by assuming that half of all the motor losses at rated load are accounted for by the armature copper loss. Means at rated load, whatever are the losses in the motor, half of those are the armature copper loss. Okay? Is this clear?
Yes, sir.
Now the efficiency I'm using, efficiency is given by, what is the formula for efficiency? Output power divided by input power. Correct? Now this output power can be written as, what can it be written as?
Input minus losses.
As input minus losses. What will we prefer? We'll prefer to write this equation in terms of the input, because it is much easier to determine the input power of the DC motor as compared to the output power. Correct? Okay, so the output power will be equal to the input power minus the losses. This becomes 1 minus losses upon input. Okay, so I can multiply both numerator and denominator by the efficiency. This will become, by the input. Okay, so this will become efficiency multiplied by the input, that is equal to input minus losses. What that gives us? What does that give us? Losses is equal to input minus input into efficiency. Okay. So if I take out input common, it becomes 1 minus efficiency multiplied by the input. And what is the input power?
VI.
Correct. V is the applied voltage and the armature current. Which armature current? In this case, we are dealing with the nominal values. So the nominal or rated armature current of the motor.
I summation of V.
Okay, is this clear? Yes, everyone?
Yes, sir. Yes, sir.
So what are these? These are the total losses of the motor under rated conditions at rated armature current. Now we said that we can assume that 50% of the total losses, that means we multiply this by 0.5, correct? Now this becomes 50% of the total losses under rated armature current, and this is approximately equal to what? The armature copper loss. How much is the armature copper loss? Yes.
I square RA.
Is the nominal current squared multiplied by RARN.
RA.
Okay. So the armature copper loss without any external resistance at rated armature current, IA nominal square multiplied by the armature resistance RARM, that is approximately equal to 50% of the total losses taking place inside the motor under rated armature current. Okay. So this is the equation that we get: 0.5 into 1 minus efficiency into V multiplied by IA nominal. So from this, we can determine the armature resistance. The armature resistance will be approximately equal to 0.5 into 1 minus eta nominal into V into IA nominal divided by IA nominal squared. So it becomes V upon IA nominal. Is this clear? Yes or no?
Yes, sir.
Yes, sir.
Okay, so this is the equation for determining the armature resistance. Our armature is approximately equal to 0.5 into 1 minus. This is the nominal efficiency, okay, efficiency under rated conditions, multiplied by V into IA nominal. Okay, is this clear, everyone? So if we know the value of armature resistance, we can find the no load speed, that is given by E upon V minus rated current into armature resistance multiplied by the rated speed. Okay, can I move forward? So this is how we can determine the natural characteristic of the DC shunt motor. First of all, we find the rated speed. and the rated torque by using torque is equal to rated torque is equal to C multiplied by the rated armature current. From that we get this point. At this point torque is equal to 0. We simply have to determine the no load speed. We have just seen how to find the value of omega 0. So we get these 2 points and then we draw a line through these points that becomes the natural or rheostatic natural characteristic of the motor. Okay. Once we have the natural characteristic, we can anytime draw the rheostatic characteristic for any external resistance inserted into the circuit. Once again, for that we need 2 points. The first point remains same. This point omega 0, this point does not change, it remains same. The other point, this point remains same. The other point needs to be found. How can you find this point? Yes. Do we know anything about this point? Do we know the torque at this point? Yes or no?
Rated torque.
Yes, it is the rated torque of the motor. Correct. This torque is the rated torque. All that we need to find is the speed at this point. Okay. And how can you find out the speed? You can find the speed by using this equation, omega with rheostat inserted into the circuit at rated current, because the torque is rated. That is equal to omega 0, that is the no load speed, into 1 minus IA nominal by R. I'll simply write R here. Here R includes the armature resistance as well as the external rheostatic resistance divided by. Okay. This is how you can find out the value of speed at this point. Okay. It is given by the no load speed omega 0 multiplied by 1 minus IA nominal into R divided by B. Okay. How this equation has come, we'll see later. I'll show you later. Okay. Is this clear? Yes. To draw this characteristic, we have this characteristic already. To draw this characteristic, all that we need is the value of speed at this point, and the speed at this point is given by the equation omega 0 into 1 minus rated current, because the torque is still rated. So the current is also rated, multiplied by the total resistance of the armature circuit divided by B. Okay. Yes or no?
Yes, sir.
What has changed here as compared to the above line? As compared to this characteristic, what has changed here in this equation? Omega 0 is still same. The rated current is still the rated value. P is still the supplied voltage. R, but now R is, earlier R was only the armature resistance. Now R is the armature resistance plus the
Rheostatic
Yes, yes, sir. Increase the value of means resistance increases.
Yes.
Slope is increasing.
Okay. I think I'll stop here. Lot of equations are there. It is better that the next class I write the equations first, and I will be wasting our time here. I'm writing all these equations. So we'll continue further in the next class. Okay. Stopping the recording.